Hello everyone. Our today's speaker is Snehalata Sahoo. She is a Ph.D. student at IIT Indore working with Professor Sanjeev Singh. Today she is going to talk about classical special functions, history and applications. You can start, Sneha.
Thank you. So before starting, I will say that I will give the overview. Then we will discuss about two special functions. And as we see that from the topic that we are talking about special functions. So why this function are special? Turan said that we can say this special function as useful function because of their remarkable properties and sorry, 1 minute. Okay, sorry. Is it visible or no?
Yes, we can see the slide. Why special functions?
Yeah, yeah. So Paul remarked it as a useful function because of its property, as it is useful in so many fields like physics, engineering, and number theory. So as it has ancient roots, as you can see that series of cosine and sine was known to Madhava in 14th century long before it was rediscovered by Newton and Leibniz. And this field has major contribution by Euler, Legendre, Laplace, Gauss, Riemann, and Ramanujan. Now, as this field is so big and there are so many special functions, now how means how we can unite this subject. So we should have a thread which connect we can find a thread which can connect so many special functions. So one of the thread is hypergeometric function because it is appearing in so many areas like calculus, physics. We may know or not know they are uh, a hypergeometric series we are using unknowingly. So understanding that it is a hypergeometric series make this complex problems little bit simpler. Now, what is hypergeometric series? It is the ratio of successive terms as a rational function of index n. Now, how it is appearing? It has connection to calculus, Bessel functions. We know that Bessel function are so much complicated function. It is a solution of second order differential equation and it's very complicated. But it can be also written as hypergeometric function when writing about its series thing. So recognizing them as a hypergeometric function is a key understanding to their elementary properties. Now, a hypergeometric world, in that world, first early discoveries were done by Euler by giving um, integral representation, and then Paf gave some transformation formula, and then Gauss given a beautiful formula as we will discuss in the further slide. Riemann connected hypergeometric function and differential equation, and Barnes gave a contoured integral approach. Now, that hypergeometric function has two signature properties. They satisfy some special satisfy identities for special values of function. As I was saying that Gauss given a beautiful formula, it has it is giving some at special value. It is giving some identities, and they have, as I was saying, Paf has given transformation formula. By transforming, they are connecting hypergeometric function to other hypergeometric functions. So it is used in pure mathematics to high-speed computation. Now, in modern horizon, they are used in Q series. We can say, what is Q series? It is the ratio of successive term, and it is a rational function of Q to power n. As we said that it is a rational function of index n, here it is a rational function of Q to power n. it is used in number theory and in physics also. Now, what is gamma function? Why gamma function came into the picture? Because we talk so much about the hypergeometric function. To read the hypergeometric function, we need a prerequisite which will be helpful to read the hypergeometric function. So gamma function and beta integral are the prerequisite for hypergeometric function. Now, how gamma function came into the picture? In 1720, Bernoulli and Goldbach posed a fundamental question that how can the n factorial, which is defined for non-negative integer, can be generalized into a continuous function of variable x. Okay. So for answering this, Euler find a function that interpolates the factorial, and they discovered gamma function, which is very important in the field of mathematics. Now, this gamma function that interpolates non-negative integer and give interpolates n factorial, and means at non-negative integers they give factorial value, and at other point it has some limiting value, so which is given by this. As x factorial can be written as x plus n factorial by this, and the denominator is nothing but a shifted factorial notation. So x factorial can be written as this two product, and the second product goes to 1. The limit of second product goes to 1. So x factorial can be written as this limit n tends to infinity, n factorial n to power x by this. So this limit exists for any complex number x that is not a negative integer. So this is the limit definition for gamma function. Now, as we can see here that gamma function has poles at negative integer and 0. No, so and gamma function is never 0. So 1 by gamma function is an entire function with zeros at this point. And we know that every entire function has a infinite product representation. So this is the infinite product representation. So now we know the gamma function. It has relation, gamma function has relation with other function, as I was saying. Now we will see that before Euler, Wallis was trying to get a expression for pi. He was tackling with this integral 0 to 1 square root of 1 minus x square. So he, while doing the calculation, he was getting the value for this integral 0 to 1 x to power p 1 minus x to power q for integer value of p and q, and when q or q equal to 0 and p is rational. So he did some calculation that is not clear, but because he didn't use gamma function, that time gamma function was not known, so he did got the value. But as we know the limit, it can be written like this, and in terms of gamma function. So this give Euler a idea that how we can use this integral and relate it to gamma function. So as you can see, this was the groundwork for beta integral, to relate gamma function to the beta integral. Now the beta integral is defined as this, and it has a relation with this gamma function. And using this beta integral relation with gamma function, Euler gave a famous integral representation, that is this, which is defined for real z greater than 0. Now, we can see in Euler reflection formula, they are relating gamma function to a sine trigonometric function. So this was the beauty. Now, for larger value of x, they give a approximate value of gamma of z. Stirling gives the asymptotic formula for gamma of z, which is used in physics statistics. When we are doing asymptotic analysis and finding limit for larger values, we use this formula for gamma of z. Now, as we know that the interpolation, what the question was, to find the function which interpolates at n factorial. So, that interpolation may not be unique. So, there may be so many functions which interpolates at n factorial. So, to give that function is unique, they added one more property which is more so strong, that is log convex property. So what is this? Give the theorem that if a function has these three properties, then the function is nothing but gamma of x. Now, how this gamma function is appearing? It is appearing in the functional equation of Riemann zeta function, and it is also has been used in proof of Fermat's theorem. Now, as I said before going to hypergeometric function, we should know the gamma function. Why? Here is the thing. It directly appears in the definition of the coefficient. As Polynomial symbol is arising in hypergeometric function, so Polynomial symbol can be written as gamma function. And we will see further that many integral representation and transformation formula for hypergeometric function is having gamma function. So now we will move to hypergeometric function. So hypergeometric function, as I said, it is the ratio of Cn plus 1 by Cn as a rational function of n, and we will approach by three way, like Euler integral representation, second order linear differential equation, and Barnes contour integral. Now, Cn plus 1 by Cn is defined as this, and summation n equal to 0 to infinity Cn can be defined as this, where it is written as PFQ. This notation is known as hypergeometric series. Now, as we are seeing series, we will talk about its convergence. So,
Sneha, sorry, can you go back? I missed CN. Where are these coming from?
yeah.
Can you go back to the previous slide also? Okay. Okay.
Can I
Yeah,
go?
you can. Yeah, you can go ahead.
Now, the behavior of this representation depends on the parameter P and Q. Okay. So when P is less than Q, the series converges absolutely for all x. When P is equal to Q plus 1, it converges, but for mod x less than 1. Absolutely, but for mod x less than 1. When P is greater than Q plus 1, it diverges. Okay. Now, we have the famous Gaussian hypergeometric function, which is 2f1, given by this series formula. And by previous slide, as we said, it converges for mod x less than 1. Okay. Now, when we say hypergeometric function, we talk about this function. When we say hypergeometric series, we talk about that series we discussed earlier. Now, what happened when mod x is greater than equal to 1? As we can give from example, this log 1 minus x has this representation, and the series has convergence in mod x less than 1. But the function is defined for larger domain. Here come the analytic continuation. So we will extend the domain. So So this is the where the analytic continuation comes into the picture. Now, so we have to find the bridge between the integral and series. So Euler gave a this integral representation for 2f1 in the we had the series form. Now Euler gave a integral representation for this form. Okay. Now this function has some properties. It provides analytic continuation of the series beyond mod x less than 1, and it shows that this function has four variables a, b, c, and x. And we can see that we just can't talk about the analyticity of this at x. We can talk about at other variables also. So 1 by gamma of c, 2f1 is an entire function of a, b, c. Okay. Now moving forward. So as I said, Gauss given a beautiful formula for x equal to 1. At x equal to 1, it is this formula, which we can see it is a gamma function, ratio of gamma function, and it is defined for this condition, real of c minus a minus b greater than 0. So means we have to connect the special, means hypergeometric function is also connected to gamma function. As I said, that's why we need gamma function to read first, and then we can talk about hypergeometric function. Now, what happens when the numerator has negative thing, means a equal to minus n? Then the series will, means after some time, that it is a shifted factorial thing. So after some time it will become 0. The infinite series will now become a finite series, and which has given by Chu, uh, which is given by Chu, as you can see this formula. Now we want to connect different hypergeometric function, as shown in the previous slides, that it has 1 minus xt mm, uh, term. So it makes it multi-valued function. So we have to restrict the domain to make it single valued. So this is the function. And one more beautiful thing is, you can see inside also it is 2f1. It is connecting hypergeometric function to hypergeometric function. Now, as I said, Riemann gave a connection to the hypergeometric function to the second order differential equation. So, uh, what kind of second order differential equation solution is hypergeometric function? It is this. Excuse me. So this is the differential equation with three singular points and satisfying this. So when we do the transformation of singular points as 0, 1, and infinity, alpha, beta, gamma by 0, 1, and infinity, we will get the hypergeometric differential equation. We will first, what we will do, standardize the singularities 0, 1, and infinity. Then we will uh, transform the
Sneha,
solution. Yeah.
sorry, can you go back to the previous slide once? Uh, okay, okay.
It general form. We will now put alpha, beta, gamma, that three singular point at 0, 1, and infinity. Then we will get the hypergeometric differential equation.
Yeah, okay, you can
We
go
will
ahead.
do the substitution, and then we will set the exponents to 0. Then we will get, after simplification, we will get the this hypergeometric differential equation. Akansa, is it fine?
Oh, yes, yes.
Yeah. So this is a hypergeometric differential equation. Now, it is a second order differential equation. So we will have two solutions. One is 2f1, okay, and other is x to power 1 minus c, this 2f1. Now, at other singularities also we will find solution, pair solution. How? At x is equal to 1, we will take, as you can see, we will set a new variable z, and that is 0 when x is equal to 1. And by how we are defining z? Z is equal to 1 minus x. And then we will get the same differential equation and we will get the solution. Now at infinity also we will do the similar thing. We will take a new variable and z equal to 1 by x, that transformation, we will get the solution. Now, as I said, hypergeometric function is related to elementary function also, special functions also. We will see there are this function which means log 1 plus x can be written as this, and tan inverse x is written as this, and then sine inverse. Okay. Now there are other special functions which is uh, related to hypergeometric function, which has this representation, and we can sorry, you can refer to this book, as it has collection of formulas, and where they have taken the formulas from. This is a very useful book who are working on the field of special function and complex analysis also, and other fields also. It is a collection of functions. Okay. This is other special function which can be represented as a hypergeometric function. Thank you.
Okay, so does anybody have any question?
Hi Sneha.
Yes.
Uh,
Hi.
can you please go back to that slide where you make it as a single valued function by restricting the argument? I just want to understand that one.
Yeah. Hmm.
Yes, this one. Okay. So here we are taking P equals to 2 and Q equals to 1.
Yeah.
Okay.
You can relate to this previous
So
formula.
I mean, whether the whether all these things which we are choosing, like, okay, anyway, argument of 1 minus x is less than pi, that is fine. But so whether it will work for every p and q, or whether, I mean, I don't know. Maybe I'm not following the definition properly, but I just want to know. So whether the same domain will work for every p and q?
We are talking about here for p equal to 2 and q equal to 1, not
Okay.
every p. I
Uh,
said that when talking about the convergence of the thing here.
okay. Okay.
Yeah, that one slide we said, na, P is less than equal to Q, then it converges absolutely. From there, not every P and Q it is going to.
Okay. Okay. C is
I
convergent
mean,
for x.
so you had taken the value, so 2, 1, right? P for P and Q.
Yeah.
So there you were saying that, so for analytic, as far as I remember, you were talking about analytic continuation
Yeah.
and some domain. I think, Abhishek, are you asking if the same domain works for
Yeah,
other
other p and q means
valid P and
other,
Q?
yeah, other valid p and q. Yes.
Hmm.
P and Q equal to 2, it is not known till now. So we can't say I am talking about P equal to 2 and Q equal to 1, particular case.
Okay.
Yeah. In my knowledge, it is not known.
Okay, okay. Okay, yeah, this is from my side. Yeah. Thank you.
Thank
Can
you.
you go back to the differential equation? There was this theorem.
Yeah, yeah. Yeah, this theorem or
Yeah. Okay. No. Go back. Go back.
okay, this one.
Okay. So this is you were giving this differential equation and putting some values for alpha, beta, and gamma. You were getting some other differential equation for which the solution was
There
uh,
only.
yeah. So
This is a general form, Akansha. We will give
okay.
a beta and gamma, and then we
Uh,
will do some computation, and
uh,
then we will get, as I said, na, we have to this take this term.
okay. 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 So its solution is this 2f1 function.
Yeah,
Okay.
means we will
Uh,
give singularities. Particular alpha, beta, gamma is the singularities. This alpha equal to 0, beta equal to 1, and gamma equal to infinity. Then we will get the after some transformation, we will get the differential
so for
equation.
other again for other values of p and q, these things are not known in full generality, is it? Um,
Uh,
like for example, this 2f1 is the solution of this hypergeometric differential equation that you just mentioned.
Yeah, other values of P and Q, from my knowledge, I think it is not known.
Okay. So what is so special about this particular case?
It it is a it is a means it is connecting to other, as shown in it is connecting to so many special functions. As you can see,
Okay.
these are
Okay. Ah.
connecting to elementary functions also, special functions also.
Okay, so in everywhere mostly 2f1 is coming, is it? Okay, no. So for example, here 0f1 is coming, 1f2 is also coming, 1f1. Uh,
So we will do the transformation and we will get again to the same as we did now. We will do the transformation and we will get to the 2f1.
okay. Hmm.
But I think her question is like that. Similarly to F1 also, like this one F1, 0 F1, they also satisfy some second order differential equation, if I understood. Not the same, but they will also
Hmm, hmm, hmm,
satisfy
hmm.
second
Huh,
order differential equation. Yeah.
maybe it will satisfy, up to my knowledge, maybe it will satisfy by doing some transformation, I think.
Yes. It
Okay,
should be, I
yeah.
think.
Hmm. Is there any other question?
So can we write a n degree polynomial in 2f1?
Any polynomial is 2f1.
Miss, I'm asking if can we write the n degree polynomial in terms of 2f1? Like here are all the function are means very
Yeah,
complicated. Means
uh,
can we
sorry,
write
sorry.
simple like
Uh,
x power n?
yeah, I'm saying that only. As I
Uh,
said, na, the numerator, that Chu has given one notation, as I said. One minute. There is Chu. Yeah, when that numerator is
mhm.
negative, then it will terminate and it will give a finite sum. So it is
I
going
see.
to be.
Okay, then it will follow from
Yeah,
that. Okay,
yeah,
thank you.
yeah. First numerator is negative, then it is going to terminate after some value. So it will
Yeah,
give polynomial only. Okay.
agree, right. Yeah.
Yeah.
Mhm.
Is there any other question? Okay, so then we can thank the speaker. Thank you, Sneha. It was an interesting talk. And yeah, thank you.
Thank you for inviting. Thank you.
Okay, so now we can end the meeting.
Yeah,
Yeah,
sure.